The next topic I'm going to talk about diode. Diode is also called PN junction, because a p-type material, diode is formed by using a p-type material and n-type both of them are semiconducting material, by the way. So p-type semiconducting material, n-type semiconducting material combined together to make a PN junction, also called PN junction diode. A PN junction diode is a two-terminal device. So here is the one terminal we call anode, another one is cathode. Okay, so here is a symbol for diode, anode and cathode. That's a two-terminal device. When you learn PN junction diode in electronics, usually the forward, they can handle up to 40-50 volts and they can handle a milliamperes of current. But when it comes to the power electronic devices, okay, the power diodes they can handle, those are general purpose, they can handle up to 6000 volts, 4500 amperes. That's a huge amount of voltage and current, huge amount of power basically. So if you look at power, P equal to V times I times cos theta. Cos theta, if I take that as 1 unity power factor, so they can handle 6000 times 4500, which is equal to approximately 27 megawatt. Okay, that's a huge amount of power. Okay, so they can handle huge amount of power. So when it comes to the diode, three categories: one is general purpose, another one is high speed, how fast they can recover. So they can handle up to 6000 volts and 1100 ampere. Here, when say high speed, the reverse recovery time is around 0.1 to 5 microseconds. What is reverse recovery time? I'll talk about it down the line, maybe in 3-4 minutes. Now, the third one is Schottky diode. Okay, Schottky diode. Okay, the Schottky diodes, they can handle only 100 volts and 300 amperes. Low on state voltage, voltage drop. When it comes to the regular diode, it can take, the voltage drop is up to 0.7 volts. When it comes to Schottky diode, the voltage drop is around 0.3 volt and the response time is fast. Okay, now the voltage drop across power diodes varies between 0.5 to 1.2 volts. I'm talking about the general purpose and high speed diodes, but when it comes to this Schottky diode, it's going to be 0.3 volts. Now, diode, as I mentioned, it acts like a uncontrollable switch. Okay, so uncontrollable in the sense, now when it comes to power electronics, it's all about control. How do we control the power flow? Diode, we cannot control it. When it is forward biased, it acts like a closed switch. Reverse biased, act like open switch. Okay, so it's uncontrollable device, and it is made with the semiconducting material. As I mentioned, there are silicon material. Basically, if you take a silicon material, add some impurities. So if you add a pentavalent impurity, we will end up with more number of electrons, made n-type material. And if you add a trivalent impurity, that means 3 valence electrons, so we'll end up more number of holes. Okay, so a p-type is, we'll say, positive, n-type is negative. So basically there are more number of electrons here, free electrons, majority carriers also called. There are few holes called minority carriers. In p-type there are more number of holes and few electrons. So holes are the majority carriers in p-type and electrons are the minority carriers. Okay, so this is anode, that's cathode. So when I apply forward biased, so when I apply a forward voltage, okay, a higher voltage to the anode, so this is positive. Okay, and holes, in reality they don't have any charge, but I can take that as a positive charge. So positive repel, and when I apply negative to the n-type material, the repel, so this junction is going to break down. There is a current flow in that circuit. Okay, that's called forward bias. Now for the same PN junction, okay, now if I connect it in reverse biased, Okay, so here is the negative and I'm connecting to the positive terminal. So what happens, they attract each other. So here the barrier in the middle, it's going to be widen and widen, so it will not allow any current in it through it. So basically in reverse biased condition it will act like a open circuit. When it comes to the ideal characteristics, okay, so this is the VI characteristics of a diode. In forward biased condition, voltage drop across equal to 0, I must be greater than 0. In reverse biased, I equal to 0, voltage must be less than 0. This is ideal case. When it comes to the practical case, so as I mentioned, a forward biased, it will act like a closed switch. Reverse biased, act like an open switch. Now, when it comes to the practical diode, okay, actual diode or practical diode, there is a small voltage drop between 0.3 volts to 0.7 volts. Okay, nowadays the current manufacturing, I think it's around 0.5 volts. Even when you test in the lab, I think you will see around 0.5 volts. At the same time, the price of this diode is less than a quarter. Okay, and if you buy a whole bunch, you might get it for a penny. So that's the reason. That's the reason they don't care much about the voltage drop as long as in between 0.3 to 0.7 volts. Most probably you can take that as a 0.5. Okay, so it needs around 0.5 to 0.7 volts to turn it on in the forward biased. In reverse biased condition, it will act like a open switch, but there is small leakage current. So this gap here, that's a leakage current. Okay, now that this is VGK, also called Zener new voltage. If you pass that voltage, if you apply bigger than that value, that's also called PIV rating, then the diode will permanently damaged. Okay, so PIV rating is nothing but peak inverse voltage rating, maximum negative voltage across the diode to avoid breakdown. Okay, now in the forward biased condition, this is the current passing through the diode, ID equal to IS, where saturation current, IS is nothing but saturation current. That value is in between 10 to the power of minus 14 to 10 to the power of minus 18 ampere. Okay, I think for our examples, I'm taking this as 10 to the power of minus 15. Okay, not 5. I think it's 10 to the power of minus 15 ampere. N here we call it a scaling factor. Usually manufacturer will give you that value is in between 1 and 2. We'll take it as 1 to solve the examples. VT is the thermal voltage. Okay, so the temperature, according to the temperature. So when it comes to the semiconductors, as the temperature changes, the number of free electrons available in that material does change. So that's what we're calculating here. That value is around 25 millivolts at 20 degrees centigrade. So at room temperature, it is 26 millivolt at 25 degrees centigrade. Where K is Boltzmann's constant, that value is 8.62 times 10 to the power of minus 5. T is the absolute temperature in Kelvin. Q is the charge of the electron. So based on that, you can find the forward current passing through the diode. Now, so in electronic circuits, we never talked about reverse recovery time in a diode. Now, but here, this part is important. So the reverse recovery current in a diode. When a diode turns off, the current in it decreases and momentarily becomes negative before becoming 0. So what we are talking about here, when a diode turns off, the current is supposed to be 0, but instead of getting 0, that value is going to go back a little bit. Okay, and then after some time, it's going to be 0. That some time, probably we are talking about microseconds. Okay, so the duration is called, we call it as, represent with T suffix RR, TRR. The reverse recovery time is usually less than 1 microsecond. And this phenomena may become important in high frequency applications. When we look into the high frequency applications, the diode needs to be, say, if you go with kilohertz, the diode needs to be turn on, turn off maybe 1,000 times. Okay, so in that cases, this TRR is very important. The next one is Schottky diode. Okay, here is the symbol for Schottky diode. This is also two-terminal device, anode and cathode. Okay, so the characteristics of Schottky diode is drawn right here. It needs only less value, around 0.3 volts. Okay, 0.3 to 0.5 volts. Schottky diode have a metal to silicon barrier rather than a PN junction. So here, instead of PN junction, for anode is connected to a metal. This is metal. Okay, and this is n-type material. This is n-type material. Okay, where more number of electrons in this material. Now for the metal, we use either chrome, platinum, tungsten. Okay, the advantage is low voltage drop across this and the fast reverse recovery time. Disadvantage is, I think I showed you already here, it can handle only small amount of voltages and current, small amount of power. It can handle only small amount of power. That's about the Schottky diode. There are different ways to pronounce, I think, Schottky diode. That's how I pronounce it. Okay, I will stop this video here. Next video I'll talk about thyristors. Thank you.